So then, hello everyone, and welcome to today's seminar on interval methods and control engineering. On behalf of Andreas Rau, it's my great pleasure to welcome today Michel Kieffer, who is a full professor in signal processing for communications with the University of Paris-Saclay, and a researcher with the Laboratoire de signaux et systèmes of CentraleSupélec in Gif-sur-Yvette in France. He will talk about the guaranteed characterization of exact non-asymptotic confidence regions using interval analysis. So without further ado, I hand over the microphone and the floor is yours.
Yes, thank you very much for this nice introduction, and thank you for coming to this presentation. So this will be a more estimation-oriented presentations and control-oriented presentation, but estimation, this is necessary for control. So what we consider is a classical setup where we have a system here on which we are measuring some data here, and what we are trying to do is to represent the behavior of the system using a model, which parameter vector is P, and the output is Y at time t. And our aim is to perform this estimation considering this noisy data. So this is a classical problem. And usually it is addressed via the minimization of a cost function where you try to minimize the norm between the measured output and the model output, and you try to find the vector of parameters that minimizes this quantity. Okay, and the estimate is the argument of the minimum here of J of P. The main difficulties are several difficulties. First, in some situations, the parameters of the model may not be identifiable uniquely. This is when you have only local structural identifiability or non-identifiability issues. And this can be observed, this can be obtained when you have different values of P hat, which lead to the same value of the model output. You have also numerical algorithm, which may get trapped at local minimizers. And even if you have obtained an estimate such that the output of your model for that estimate is relatively close to the system output, it cannot be considered as a final answer, and a quality tag is missing, and this is why you need to obtain an evaluation of the uncertainty. For example, in that case, this is very accurate, and it's much more accurate than this case. So I will start with a brief overview of some ways to obtain the characterization of this uncertainty. And so we are not that many. Do not hesitate to ask me questions, to interrupt me when you have doubts and or when something is not clear. So there are several classical approaches to characterize uncertainty. Some are based on level sets. You try to consider, to evaluate, to look at a given level of your cost function. Monte Carlo techniques are used. Some are using evaluating the density of the estimator using, for example, Fisher's information matrix. You have also bounded error estimation, which are able to provide sets which can serve as an estimate of the uncertainty with which you have characterized your parameters. But one of the shortcomings of all these approaches is that most of them are if not all of them, try to characterize the uncertainty, but they rely on hypotheses of the noise which are corrupting the data. And this assumption of the noise, you have to make them a priori. For example, you have to assume that the noise which has corrupted the data is Gaussian with a known variance. And you may verify this assumption afterwards, a posteriori, once you have performed the estimation of P hat, considering the vector of residuals. This means the difference between what you have observed and the output of your model. And from that, you may hope to estimate the characteristics. You may verify the distribution of the residual and have some idea about the distribution of the noise which has corrupted your data. But in fact, this is quite difficult to verify when n, y, the number of measurement, is relatively large, and it's impossible to verify when you have only a few data points, let's say 10 or 15 data points, when you have 2 or 3, even as few as 2 or 3 parameters to estimate. So, nevertheless, there are some situations, even if you have a relatively few amount of parameters, when you have some knowledge about the distribution of the noise, you are able to characterize confidence region even with a few amount of measurements. So I will here remind some relatively old results about, for example, the situation where we consider that we have wide Gaussian noise with known variance. This is a situation we'll start. So we assume that the prediction residual, the difference between the model, the model output and the measurement, satisfies for the true value of the parameter. This is y star. I assume that for the true value of the parameter, I have only here the noise. And I assume that this noise is IID and Gaussian distributed with zero mean and variance sigma square with known sigma square. Okay. Then in that situation, the maximum likelihood estimation leads to the minimization of this. I have simply to minimize the squared residuals. And for the true value of the parameter vector, what remains here is only the measurement noise. And in average, the value of the criterion at the true value of the parameter, more or less, in average is equal to nt times sigma square. So this is interesting because it is useless to try to consider a value of the criterion below nt sigma square. And what we also observe that the larger sigma square, the higher the isocriterion we have to consider if we want to characterize the confidence region. So the noise, in fact, raises the maximum acceptable value for the criterion. But we can be clearly more precise than that. If we consider the vector of the prediction error, we know that these vectors evolves in a space of the dimension nt. We have nt component. It evolves on the surface of dimension nt. And now if I consider the value of the criterion divided by sigma square, I normalize the value of my criterion. Here, I obtain the sum of the square of nt Gaussian variables. And the sum of the square of nt Gaussian variable is distributed according to a key2 distribution with nt degrees of freedom. So now, for such kind of distribution, I can introduce that variable. This is the value that has a probability alpha to be exceeded by a random variable, which is distributed according to a key2 law. Okay? And from that, we can define a confidence region with a level 1 minus alpha% as the set of all values of the parameters such that the cost function is less than sigma squared times key2 alpha. And this defines, for example, if you take alpha equal 0.05, this leads to a 95% confidence region. We can illustrate this. For example, I take the hello world nonlinear estimation problem. Here we have you have two parameters, P1, P2 to estimate. This I have chosen the true value of P1 and P2 like that. I have generated 64 measurements, added some Gaussian noise with variance sigma square equal 0.01. And typically, we are able to characterize the set that has been defined here, this set using interval analysis, and we are able to obtain this set here. In green, these are boxes which are guaranteed to belong to the set, red boxes which are outside, and in yellow you have small boxes which are at the boundary. So we obtain, here we are able to characterize a set which corresponds to the confidence region. Here, this is a 90% confidence region. Now we go to a little bit more complicated setup. Now we consider that for the true value of the parameter here, the noise is still Gaussian, IID, but now the variance is unknown. We are in a situation which is a little bit more complicated. And clearly, we cannot use anymore the previous definition, since here we do not know sigma square. Sigma square is unknown, and we have to be able to define confidence regions without the knowledge of sigma square. We still know that the noise is Gaussian. So the main idea is to look at what happens in the data space. And if we consider the data space, here this is a model, this is a space of dimension nt, we can represent the measurement as a point. Here, this is y. What we have also is the set of points which is described by the model output. Here, this set of points, ym of p, they evolve on this surface here. This is a surface response of the model. And when the model is linear in the parameter, we have an hyperplane. And when the model is nonlinear in the parameter, we have an hypersurface. And the maximum likelihood estimation in that case corresponds to the projection of y on the surface response of the model. Typically, we obtain that point here. Okay. And if we introduce the projection matrix, this is a projection which performs this projection here, which evaluates the projections on the surface response of the model. Here, we have, as before, we have the dimension of p, which is np, the dimension of y, which is nt, and this is the error. Then here, the criterion at the true value of the parameter, it's still the sum of nt, the nt squares of Gaussian variable, and it is distributed according to sigma squared times the chi-square distribution of nt degrees of freedom. But what is interesting is if we consider the orthogonal projection, the projection on the surface response of the model and take the scalar product with the residual, what you obtain is, in fact, this is distributed according to a chi-square distribution with now np degrees of freedom. And the same, if you consider the orthogonal of this, you consider the orthogonal of the error, and you make the scalar product with the residual, then you obtain a random variable which is distributed according to a chi-square distribution with nt minus np degrees of freedom. And afterwards, you can compute the ratio between these two quantities that are independently distributed. If you perform the ratio between these two quantities, you obtain a new random variable, which is now distributed according to a Fisher's net core distribution with np and here nt minus np degrees of freedom. Okay, here now you are rid of the unknown variance. And you can again define a confidence region. What we introduce is f of alpha. This is a value which has a probability alpha to be exceeded by a variable distributed according to a Fisher's net door law. And you can define a confidence region as you have defined the confidence region previously. It's a little bit more complicated. Well, we could think then we could apply again interval analysis. Unfortunately, in that case, this is much more complicated, and the main difficulty comes from the definition here of the projection matrix which is involved, where you have the inversion of a matrix to evaluate. And this inversion of the matrix makes the computation much more complicated. So for the time being, it's still an open problem to perform the characterization using interval analysis. We can perform characterization using gridding, but not using interval analysis. I switch now to more recent ways to characterize estimation uncertainty on confidence regions. These are the techniques SPS and LSCR, which were introduced by Campi and his co-workers. And the main advantage of both of these approaches is that you are able to obtain exact confidence regions, an exact characterization of the parameter uncertainty, and also in non-asymptotic conditions, as we have seen in the previous two approaches. And the main advantage of this is that these approaches rely on relatively mild hypotheses on the noise and on the system. The first hypothesis, I assume that the system which is generated the data, it must belong to the model set. So the true value here should be meaningful. And we assume also that the noise samples should be independently distributed with a distribution which is symmetric with respect to 0. So probably the strongest assumption, this is an independent distribution. But if the distribution is not independent, there are tricks that may be used on the more recent papers that address this situation. But one of the main hypotheses is here that the distribution has to be symmetric with respect to 0. Okay? So from now on, I will detail both of these approaches and see how we can characterize the confidence regions using defined by these approaches. So I will start with SPS. So SPS stands for sign perturbed sums. The main idea is this type of approach is designed for models which are linear in the parameters. So we assume that we have a linear regression model, a model linear in the parameters, which is corrupted by some noise. And here phi, this is a known regressor vector. Then, in order to estimate, to evaluate the estimate p hat, in that case, usually when you consider, for example, least square estimation or maximum likelihood estimation in when the noise is Gaussian, what you have to do is to solve this normal equation here. This is a way to obtain an estimate. And SPS tries to obtain a confidence region for P star around this least squares estimate. So you do not make any assumption, any additional assumption on the noise, except that it is symmetrically distributed, centered around 0, and that the noise samples are independent. So for that purpose, we introduce this function S0. This is simply the normal equation, which has to be 0. And afterward, we also introduce the sign perturbed sums. This is simply a variant of S0, where we have here introduced a random variable, a binary plus or minus 1 random variable with equal probability. Okay? And afterwards, we evaluate Zi, which is the norm of the Si. Okay? And there is a property we can show that the norm, when you order the Zi evaluated for P star, when you order them in increasing order, then the rank of Z0, this is the unperturbed sum, should be uniformly distributed. Okay, this has been proven by Campi. And so from that, we can consider the set sigma q of all values of P such that Z0 is not among the Q largest value of this. This were the previously defined variables. And one has P star, which belong to sigma q with an exact probability, which is 1 minus q over m. So q, this is the you select all values such that z0 is not among the q largest value. Okay, on m, this is simply the number of terms, here the number of random sums that you have considered. So with this, you are able, by a proper selection of q on m, you are able to define a non-asymptotic confidence region with level 1 minus q over m. Okay, we can define this a little bit more formally here. So sigma q, this is a set of all p belonging to the search space, such that the sum of this indicator function is larger than q. And what is this indicator function? It is equal to 1 when zi is larger than z0. This means that z0 is less than zi. And you should have at least q values of zi, which are larger than z0, in order to have for p a value which is in sigma q. So here I've considered a small illustrative example. For example, we consider the very simple model ym of p is equal to p. And I have introduced I've generated 20 noisy data for p star is equal to 3. And afterwards, I have generated 10 random sign perturbed sums, okay? And all the corresponding z0, z1, z2, etc. are represented here. And what we see is that here, for values which are relatively far from the true value, which is 3, we have z0, which is above all the other values, okay? And so we can say that here, clearly, p is not in that area and does not belong to the confidence region. Afterwards, if we select q equal 1, since we have 10 generated sums, the probability is 1 minus q over m. And so here, in that case, we have a probability which is a confidence region with a level of 90%. And this is a 90% confidence region here in red. If we consider two values, you ask z0 not to be among the two largest zi, then you can define with this the 80% confidence region, which is here, okay? And you can go even below. So using this, you are able to characterize confidence regions without any additional assumption about the noise, that it is independent and symmetrically distributed. Well, the main drawback of this approach is that you have to consider models which are linear in the parameters. If you consider a model which is non-linear in the parameters, then you have to switch to another family of approach, which name is LSCR. So LSCR stands for leave out sign dominant correlated regions. And the main idea of that is, if you consider, this is again the estimation residual, if you consider a value p of the parameters, and if you consider correlations of this estimation residual, typically, for example, for an estimate, you know that the value of p that you estimate should make sure that the epsilon of t should not have always the same sign. Intuitively, the error should not, you should not have always the same sign. And if you evaluate, if you consider, for example, a value such that an estimate, value of the estimate p, such the epsilon of p have all the same sign, then if you evaluate the correlation among the prediction error, you will have something which is positive. Okay, since they have all the same sign, the correlation, the estimate of the correlation will also be positive. There may be all the epsilon may be negative. In that case, again, the correlation of the epsilon will be positive too. So the main idea is to try to characterize the set of all values of P such that the independent estimate of the correlation of the prediction error have random signs. And the main idea of LFCR is to leave out the subset in the parameter space where the sign does not appear random. This means that they are sign dominant. For example, you have several estimates which have the same sign, or a majority of estimates which have the same sign. Okay? And using this approach, we are again able to define without any approximation the region theta to which P star belongs with a specified probability. Here again, this is the same illustration as before. I take this model, and now I've only considered 8 noisy data which were generated with P star equal 3, and I have generated 7 different estimates of the empirical correlation. I will show afterwards how these estimates were obtained. And I would like to characterize the set where the empirical estimates of the correlation have not all the same sign. For example, here we see in that area, these are the empirical correlation. This is one empirical correlation which is plotted as a function of P, and we see that in that area or in that area, it is positive, and in that area here it is negative. And we see, for example, that in that area here, all estimates of the correlation are positive. In that area, also, all estimates of the correlation are positive. Here in that area, for example, you have some estimates which are negative, they are here, and some others which are positive, they are here. Okay? And so, with this, you can define a non-asymptotic confidence region, the way the detail will be presented afterwards. So for that purpose, first, we consider again the evaluation of the prediction error at a given time instant t. Okay. And we know that epsilon t of P star, this is a realization of the noise which has corrupted the data at time t. Afterwards, we select two integers, r and q. So afterwards, for t ranging from t plus r to k plus r, which is equal to the number of measurements, what we can evaluate is here, this is one term that will enter in the evaluation of the correlation when you consider the correlation with a lag, which is r. Okay? Usually we consider a sum over several values of t here in order to perform the evaluation of the correlation coefficient. We perform a mean. Here, in order to obtain independent estimates of the correlation, we won't make the sum over all t's, but we'll consider a partial sum. We'll compute these terms, SI. These are partial sums of these coefficients over set of indexes, and the set of indexes has to have a very specific property. I do not go into the detail while this property has to be obtained, but it has to be all this set, the collection of this subset has to be closed under the operation of symmetric difference. So here you make the union of two elements of the set, you take the intersection and you remove, you make the difference, and this operation has to be closed. So if you take any element, applying this operation, you should get an element which belongs to G. And in that case, if you evaluate this, then the probability that less than Q among the M of these of these quantities here evaluated at P star, that they have different signs, is exactly 2q over m. So restart. The probability is then less than q among the m terms that you have evaluated at p star have a different sign. This is exactly 2q over m. So then what we can introduce is the set theta such that at least q function s are larger than 0 and at least q function are smaller than 0. And with this set, you are able to show that the probability that p star belongs to this set, this is exactly 1 minus 2q over m. So before, this is simply an example of the construction of this index set. For example, you have the first index where you will take the first estimate of the correlation, second, third, fourth, first, second, fourth, fifth, first, third, fourth, sixth, etc. This is the way you form the first estimate of the correlation. Here, the second estimate of the correlation, where you select only the terms which are in black. Okay. Well, the shape and the size of theta here depends mainly on the values that you give to q. This determines the confidence level, and to r. And it depends also on the group that you can form, on the number of its elements. A procedure for generating R of the appropriate side is given by Gordon, for example. I go back to the previous example. For example, if I take Q equal 1, this means that I try to characterize a set such that I have at least one estimate which is positive and at least one estimate of the correlation which is negative. And so this is typically the set which is here in red. Here, since I have 7 empirical correlations, I get a confidence region with 1 minus 2 over 7. This is a 61% confidence region. If you consider more measurements, you are able to obtain more accurate confidence regions with different confidence levels. So you have it's less flexible than using SPS. So again, we can introduce a more formal definition. So this set here, this is an introduction of this is an intersection of two sets, theta minus and theta plus. Theta minus, this is a set such that you have the sum of this indicator functions which is larger than q, and theta plus, this is a sum that this indicator function is also larger than q. I will introduce afterwards the indicator functions. So the indicator function theta plus is equal to 1 when the estimate of the correlation function is larger than 0, and theta minus it's equal to 1 when the estimate of the correlation function is negative. Okay, so theta minus contains all p belonging to p such that at least q of these functions are smaller than 0, and theta plus at least q of this estimate of the correlation function which are larger than 0. So now we can go back to the estimation the estimation problem, the very simple estimation problem that we have considered previously. Again, I've taken exactly the same data. And here, this is the shape of the confidence set I obtain with LSCR. The main difference with the previous approach is that I've made no assumption related to the Gaussian distribution, and I do not consider any assumption on the variance of the noise. So we are able here to characterize the confidence region without any assumption related to the probability distribution, except that it has to be symmetric. Okay, here this is only a reminder about to see what was the estimate in the previous case. So this is with the K2 distribution with the K2 level, and this is a distribution that we obtain using the using this estimate here. Okay, now I'll switch to the guaranteed characterization using interval analysis, the way this characterization is performed. So in both cases, in SPS or LSCR, what we have to characterize is the set of all values of the parameters such that we have the sum of some indicator function has to be larger than Q. And these indicator functions are given by the fact they are equal to 1 when Fi of P is larger than 0. And Fi of P depends mainly on the model structure, the measurements, the vector of parameters. And it depends also on the method that you are using. It can be LSCR, SPS. So what we have to characterize is, again, this set here. And here what I've plotted are typically example of sets where I have, for example, tau1, which is equal to 1. Here, this is tau5, which is equal to 1. Here, tau3, tau2, tau4. And what I have to consider is the set such that the sum is larger than something. If I consider, for example, larger than 1, 2, larger than Q. For example, if I consider Q equal 1, I have to consider the set such that at least one of the tau1 is equal to 1. And then it's the union of all these sets here that were previously defined. If I consider Q equal 2, then I obtain the set of all parameters such that at least 2 of these tau i's are equal to 1. So I obtain, for example, this area where I have 2 sets, or that area, etc. This is here the set, and I obtain, in that case, a 60% confidence region. I may also ask Q equals 3, and in that case, I ask that at least 3 of this set are larger than, are equal, 3 tau are equal to 1. Okay, so this can be done in an approximate way by gridding or in a guaranteed way using interval analysis. So very simply, we can characterize this, this kind of set, considering an inclusion function tau, which is an inclusion function of this sum, and apply the CVI algorithm. For example, with CVI, you consider an initial search box. You evaluate the interval provided by the inclusion function. Here you obtain a relatively large interval, which is not above Q entirely. Here you see that the set of values that you obtain is strictly less than Q, so you are able to eliminate the red box from the search area. And here you obtain a green box because you have all values which are larger than Q, so all points here belong to your confidence region. So this is the main result. Now I can either stop here or quickly go through the source localization problem. I think if you have 5 more minutes, I will go quickly through this. It's okay?
That's totally fine, yes.
Okay. So the main the problem of source localization, this is a problem which is encountered, for example, in indoor localization or when you try to localize an electromagnetic source. And there are various approaches which may be used from this, using measurements of the wave which is emitted by an object. For example, you may use the time of arrival of the or the difference of time of arrival, or the receiver signal strength. This is the last approach that I will use, and I will try to compare bounded error approaches and the approaches that we have just seen using LSCR. So the setup, we consider that we have NA anchor nodes where with a fixed location, theta I, And we have an agent situated in θ0, which emits an electromagnetic wave on an acoustic signal, which is received by the anchors. This is a measurement here. This is a case receiver signal strength measurement, which is received by anchor I. And the anchor transmits the receiver signal strength measurements to a central processing unit. So our aim is to try to evaluate a confidence region for the estimator of θ0. This is a location from the measurements which are here. Okay. So what we'll consider is a Okumura-Hata model. This is a classical model of the attenuation of the received wave. So this is a power at some reference distance d0, gamma p, this is a path loss exponent, and we see that we have a decrease which is proportional to the path loss exponent and to the distance between the object and the ice anchor. And this is a noise, and here we are in a log domain. We have a noise. We assume that the noise is symmetrically distributed in the log domain. Okay, and that the noise measurements are independent. This is okay. This is a reasonable measurement, reasonable hypothesis. This is a little bit less reasonable. Okay, this is a parameter vector. Here, for the true parameter vector, we have this, and we have this. This is the way the model output is for the true parameter vector. And so we are searching for the parameter in some region P0. For that, a reference method could be the bounded error estimation. For bounded error estimation, we assume that the noise is bounded in some interval with known bounds. And what we are searching is a set of all parameters in some search area, such that the model output is included in the measurement where you have subtracted or added the noise bounds. Okay. The main difficulty in bounded error estimation, this is a question I get every time I make a presentation about bounded error estimation, is how do you choose the noise bounds, since in practice you do not know the noise bounds? So, and the answer is, well, in some situation we may get an empty estimate, and this empty estimate may result from noise bands which are too optimistic, or the model is inappropriate, or the initial source block is too small. So in that case, we can switch to robust bounded error estimation. And in this case, we get an estimate which is very similar to the previous estimate. What we try to do is to have some indicator function here, tau, which is a sum of indicator function. And this indicator function are equal to 1 when this is satisfied, when the model output belongs to the system output minus the noise bound. And we have to select here the proper number of measurements. NA times N, this is the total number of available measurements. And here you tolerate Q outliers, Q measurements which are not satisfied, Q measurements for which this condition is not satisfied. The question here, we have still the question about E, the bounds, and we have the question about Q. So for the simulation condition, we consider 5 anchor nodes, which are placed at the corner and at the center of a square of 20 by 20 meters. We consider 20 agents. We have 20 locations, 32 locations that we try to estimate. Each agent will transmit 10 messages. So we'll have per agent 50 measurements, P0, D0, and gamma P. This has the true value of the parameters. And I will consider several hypotheses. First, I assume that the data are IID Gaussian with a noise with standard deviation 2 dBm. And afterwards, I consider a Gaussian-Bernoulli-Gaussian noise. This is a noise, a small noise with a probability of 0.9 and a high noise with a probability of 0.1. So Afterwards, I consider three estimation problem. I estimate only the location. I estimate the location on P, and I estimate the location on gamma. These are the three estimation problems. With LSCR, now you have different ways to organize the measurement. Either you consider all measurements here successively for each of the sensors, or you alternate. And well, what you have observed is that only the first way of organizing the measurements provide a confidence region which is reasonable. The other one, okay, this is not valid because you have mixed measurements that are coming from several sensors. And so I will not present all the results, but here just an overview. This is here in the column, you have the results when you estimate only theta. Here, this is a result when you obtain theta on P0. These are the result when you estimate theta 0 on gamma P. And here, these are the estimates here, which are, most of them, these are the estimates here on that row provided by LSCR, and here on the below, these are the results which are provided by bounded error estimation. For the error bounds, I've considered twice the standard deviation. And what you observe is here that the sets here are quite small or relatively accurate, while with the bounded error estimation, clearly you have to overestimate. But even if you overestimate, you have several points here, several estimates, where you have an empty set. Here you see that with bounded error estimation, the size of the set increases really a lot. And here also. This is the results that you observe, that you obtain with robust bounded error estimation. When we consider robust bounded error estimation, I simply considered 1 time the standard deviation. And again, here you have situation where you are not able to obtain by the estimation accuracy on the size of the confidence region is relatively similar to the size of the confidence regions that have been obtained by LSCR. And so you have additional results on the slides that you will be able to obtain. So I switch now to the conclusions. So we have obtained several ways to obtain non-asymptotic confidence region. Well, when you have Gaussian noise with known variance, this is perfectly suited to the characterization using interval analysis. When you have Gaussian noise with unknown variance, this is difficult and this is an interesting problem. With SPS, this is suited to model which are linear in the parameters, and we are efficient characterization. I don't detail, there are also efficient contractors. You have them in the slides afterwards if you want to look at them. And in LSCR, this applies to linear and non-linear models. And again, you get an efficient characterization. Unfortunately, you have less efficient contractors. And this is one of the direction of research of this kind of work, to define efficient contractors in order to be able to obtain the result in a minimum amount of times. Thank you for your attention. And if you have any question, you are welcome.
Yeah, thank you very much for your very interesting presentation. And the floor is now open for discussion. So please just unmute yourself if you have any questions or comments. So there seem not to be any questions.
Okay. No problem. Don't hesitate to, there are details in the papers which are in the references. And if you are interested in contractors and the basic idea about the contractors, this material is also at the end of the slides and in the Automatica paper that was published here, this is a KW14. This is the Automatica paper, which is related to that.
Okay, so then thanks again for your
Thanks a
presentation.
lot. Have a nice weekend.
Yeah, have a nice Friday afternoon. Have a nice weekend. And see you all in 2 weeks for our next seminar.
Goodbye.
Goodbye.